Welcome to this video. This is Mark Scythian. The date today is May 24th, 2019. The title of this video is Compressed Natural Gas Runtime and Efficiency Analysis for Piston Electric Generator. Now, it's not a bad idea to run gasoline piston engines off natural gas because the fuel source is already in the vapor state. There are some drawbacks though, that because the mixture is so lean, it is ideal for much higher RPMs, especially generators operating at constant speed, like about 3,600 RPM. And that's relevant to the gasoline four-stroke piston engines that you would usually run gasoline off of. Well, if you want to switch over to either propane or compressed natural gas, there are some calculations to make on the viability of doing so, if it's even worth doing so. So we're going to create a application here. So taking the concepts of thermodynamics and physical chemistry, we can know if this is even worth doing. So here's the scenario. An AC piston electric generator is operating at its rated RPM of 3,600 RPM, driving an AC brushless generator with a maximum true power output of 8,000 watts. This generator is powered by a four-stroke, single-cylinder gasoline piston engine with fuel delivery system converted to run off of a 10.5 dry US gallon compressed natural gas tank with a maximum gauge pressure rating of 3,600 psig. The piston engine has a bore of 3.46 inches and a stroke of 2.52 inches, compression ratio of 8:1. Assume that the AC electric generator has an electromotive generator efficiency of 65%. And the piston engine has an unknown brake horsepower at 3,600 RPM. The stoichiometric ratio of natural gas, also known as methane, combustion is 17.2 to 1. Propane is actually 15.5 to 1, so it's even leaner, with an energy density of 1,050 BTU per cubic feet of gaseous volume natural gas, and 21,000 BTU per pound weight of natural gas. Based on this data, calculate how long this generator will run if all 8,000 watts of AC true power are tapped, while running off this given CNG tank pressurized to a gauge pressure of 3,600 psi. Also assume that this generator and tank are operating at an air temperature of 72 degrees Fahrenheit at an elevation of 1,340 feet above mean sea level. And this is your typical 110 volt AC RMS, 8,000 watt AC true power braided piston electric generator. So again, you can use the Planck formula for calculating brake horsepower for reciprocating piston engines that are running off heat, or basically the pressure, so you can get that pressure from anything, even compressed air. But we're dealing with the pressure coming from fuel combustion. So you're going to first want to solve for the torque. So that's the most accurate BHP formula. The general one is this one right here, 6.28 radians times RPM times foot-pounds torque divided by 33,000 foot-pounds per minute. So we can rewrite that and then solve for the torque, the T compound, or component. So BHP times 33,000 is equal to this. So solve for T. So what we'll have to do is get the cubic inch displacement first. And of course that is a bore of 3.46 inches divided by 2 to get radius squared times pi. So we have a 9.4 square inch bore times a stroke of 2.52 inches. So there's 23.7 cubic inches per cylinder, or 388.37 cc displacement. So all we have to do is calculate the brake horsepower. Actually, this one here, I'm going to bypass this. It was more of a note. But we'll go to page 2. And remember, the output is 8,000 watts. That's what you're actually getting if all the load is tapped electrically. 8,000 watts AC true power. We have a generator efficiency of 65%, so 1 over 65. It's going to take 12,307 or 308 watts of mechanical power output from the piston engine to get this electrical output. So we find out what that is in horsepower, divide it by 746. We're going to need 16.5 horsepower, actually brake horsepower output. And remember that for every 1,000 feet above mean sea level, you're going to lose 3% in brake horsepower. If it's a naturally aspirated piston engine, especially like a small engine, nothing modern like switching valves like you see on cars, but typically you would keep the air pressure at sea level conditions with altitude using a turbocharger running off the exhaust, but this is naturally aspirated. So it's implying you're going to lose 3% brake horsepower per 1,000 feet elevation. So we're at 1.34 K feet, 1,340 feet above mean sea level, times 0.033% times 16.5. So we're going to need an additional 0.66 horsepower to compensate. So it's been written as 17.6 brake horsepower. And then if you do the analysis on natural gas combustion, it's a little bit better thermal efficiency than gasoline. It's about 38% thermally efficient inside a piston engine. So 1 over 0.38, you get 45. You're actually going to need 45.16 horsepower in the form of burning natural gas. Methane is actually required to operate engine output to get the 12,307.7 in order to get the 8,000 watts AC electrical power. So we do know that for every 1 BTU per second heat output, that's the same as 1,056 watts. So all we need to do is take the 45.16 times 746 watts per horsepower, get the watts out of that, and then divide that into 1056. So that's 31.9 BTU per second. And then required natural gas per second input into engine, 31.9 BTU per second. We divide that into 1050 BTU, 1050 BTUs per cubic foot of natural gas. Translates to, if you set it up right, these cancel out, and it's 0.03, about 0.03 cubic feet per second natural gas consumption. Then you have to go to the ideal gas law. Number of moles is equal to absolute pressure of the gas, fixed volume, liters, divided into that's absolute pressure in ATMs times a fixed volume in liters, divided into this constant here, 0.08206, times the Kelvin temperature, which is the Celsius plus 273. So all we have to do is calculate the atmospheric pressure here. You can use that equation again. This gets you the ATMs here, times 14.7. So if we go continue on here, we have 14 psi at 1,340 feet above sea level. So that's the same as 0.95 ATM. So all you got to do is just take the PSI, multiply it times this factor, And that would be the same as this value here, excluding the 14.7. You'd get the same thing here. That's a metric version. That's the US English version, but it works. Both of them are the same for this calculation. And so 1 US dry gallon of volume is 4.4 liters, but a wet gallon, like liquid, it would be 3.78. So you got a little bit more volume involved with the conversion of a dry gallon or a gas gallon volume. So gallon is a volume measurement, right? So 10.5 US dry gallons times 4.4. So that's a 46.2 dry liter tank, or say 46.2 liter tank. CNG, compressed natural gas volume, empty. So that's 46.2 liters. Methane has a chemical formula, CH4. So you have 12 grams per mole for carbon, 1 gram per mole for hydrogen. You add it up, your 16 grams per mole is the molar mass of methane or natural gas. We got to convert 72 degrees Fahrenheit to Kelvin absolute temperature. So subtract 32, multiply times 5, divide by 9, 22.2 degrees Celsius is 72 degrees Fahrenheit. Add 273, so we get 295.2 Kelvin. And then what you do is you take the gauge pressure. We know it's going to be 3,600 psig times the conversion factor here. And so we need about 245 ATMs of methane gauge pressure, 245 times greater than standard atmospheric pressure in compressed natural gas. Then, of course, absolute pressure is the gauge pressure plus the atmospheric pressure. So we convert the 3,600 psig, 245 ATMs, 14 psi, 0.95 ATMs, add them up. We have a total absolute pressure, 245, about 246. Let's say 245.9 ATMs absolute pressure, fully charged CNG methane tank, right? And then now you're able to calculate the moles. We use the N mole. We can use N right here. So just put 245.91 for absolute pressure times a fixed volume 46.2 liters divided into the constant times the Kelvin absolute temperature. That's 469 moles of methane gas. So then we know that 1 mole of methane gas is 16 grams. So if you just figure that out, 469 moles times 16 grams per mole for natural gas, that's 7,504 grams of methane gas. Divide that to 1,000, so it's 7.5 kilograms methane gas. So if we divide now if you go look up the density of natural gas, which should be on any chart, you're going to get 0.656 kilograms per cubic meter is the density of natural gas or methane. So take this weight or this mass of the gas charge, divide it into the density. So that's 11.44 cubic meters of methane gas has to be pressurized into that tank. So you just get the cube root of 11.44 cubic meters, 2.25 meters. 1 meter is 3.28 feet. So just take 2.25 meters, multiply it by 3.28 feet per meter, 7.38 feet, then cube that. So that's 401, about 402 cubic meters of natural gas. So I just put 401.95 cubic meters methane charged into tank equals 3,600 psig, right? And so if we take the 401.95 cubic meters natural gas and divide it into the rate that gas is going in to get that 17.16 brake horsepower, that translates to 13,270.7 seconds. About 13,231 seconds. So we divide that into 3,600 seconds is 1 hour. So you only get about 3.7 hours of runtime. However, that's at full 8,000 watts. And a lot of generators are tapped maybe half, 3/4. But let's say, it's an emergency and all the power is being tapped, and maybe the gas stations are shut down, and like gasoline and all that. Well, at least with 3,600 psi G charge into a 10.5 gallon tank, you should get close to 4 hours, say 3.75 hours of runtime. So approximately, say 3.5 hours, just to be safe. So if you want to look at the overall efficiency involved, it's 8,000 watts output, right? That's what you're getting. That's what you want. That's why you have that generator. But the input is going to be this rate of gas flow, 0.03 cubic feet per second, times 1050 BTU per cubic foot, times 1056 watts per BTU per second. So that translates into this ratio. You got to put 33,685 watts input in natural gas to get your 8,000 watts output. So it's about 23%, which is about right. Fully running on gasoline, you're probably looking about 18%, 19%. Because remember, no load thermal efficiency with gasoline is 33%. That's just to keep the engine running. And then whatever you do with that engine, you're going to go down more. So typically, if you have a generator maxed out, gasoline, 4-stroke, and you have all 8,000 running full with maybe a voltage regulator so it doesn't burn up, right? It just limits to 8,000. You might get about 16 to 18%. So this is a little bit more efficient. It is very conservative on the thermal efficiency. There's a lot of calculations where the burn rates are 50% thermally efficient. Yeah, in open air and maybe heating. But when it comes into reciprocating engines, you'll get about 5% more efficiency, about 38%, just to run the engine. And then to have that engine run at the generator, then it's going to cost a lot more. So about 23 to 24%, which is quite high given the condition. But then look at the runtime, it's not that long. So you're going to have a cleaner engine, you're going to have less carbon into the oil, you can go longer before oil change. A lot of times the oil just burns out and you have a float in there, shuts the generator off, it's the oil guard. But I'm just saying, if you got the oil under control, or you built something like an oil cooler for continuous long extended operations where you could like move the oil around, an external oil cooling system, like 4 times the oil or something, just to maximize the oil runtime. Let's say you did do something like that, like a modification, and you could run it for like 1,000 hours. Well, the oil would be relatively clean by a factor of about 2. It would be 3,000 miles in a car run on natural gas. It would be 6,000 on the oil change. So you just have a cleaner engine. But then the drawback is you don't get much runtime. And maybe for emergencies, short time, it'll work. But overall, it's just better to stick with gasoline if you can store up on that during an emergency, just enough. And I can do another analysis on the gasoline version to see the comparison. But anyway, it's a natural gas methane piston engine, gasoline 4-stroke, thermal efficiency is 38%, as opposed to the standard thermal efficiency of 33% powered by gasoline. And then after you tap all 8,000 watts, that's pretty high actually, about 24% overall efficiency. So feel free to go through and understand the concepts throughout the lecture. Many of you are already familiar, but those of you who have something to work on or you need some information, I thought this would be a video to make to get the fundamentals under control so you can go resolve your problem if it's related to the nature of this question. So thanks for watching and have a great day.